Okay, so engineers often do to design alloys with high strength. For example, yesterday I explained about this one jaw crusher, which you need a very strong and very hard steel to crush the rocks, and or if you need a pipe cleaning big brush, yeah, which is should be very ductile and also flexible. Okay, so then. Even it is the same material is it still steel, but we can engineer the metals, the properties. Okay, so the relation between dislocation motion and mechanical behavior is important in strengthening the metal, because if we can restricting the dislocation or reduce the dislocation or reduce the path for dislocation, that will make material harder and stronger. Okay, so because hardness and strength, well, even yield strength or tensile strength actually related to the ease of plastic deformation can be made to occur, then the mechanical strength may be enhanced. Okay, so if a metal for some case is very uh, it's not easy to do plastic deformation, then the metal will be strong and also hard. Okay, and then so virtually all the strengthening technique rely on these simple principles, which is we have to restrict the dislocation motion. Okay, so we have to membatasi gerak dislokasi. Okay, so restricting or hindering the dislocation motion in order to make material harder and stronger. Okay, so the first one to restrict the dislocation motion is by lowering the grain size. Let's say I have one metal that have grain of, for example, average of 10 microns. If I compare it with metal with average of grain size around 1 micron, even those two metal have similar composition, the one that have a smaller grain size will be stronger than the previous one. Okay, so the size of grain is a polycrystalline. So this is, for example, like one big grain, and this is the other grain there. So adjacent grain will have the different crystallographic orientation. Yeah, grain setelahnya ya, butir setelahnya. So the adjacent grain will have a different orientation. So when we have the dislocation motion in this grain, in this slip plane, and this is the half slip plane, and then up to here we have to change direction in order to pass the next grain. Okay, so and the atomic disorder within the grain boundary will result in discontinuity of slip plane from one grain to another. Okay, so if you have a smaller grain, that means you will have more of the boundary, the grain boundary. Okay, if you calculate it, so it will also restrict the dislocation motion. Okay, so this is we call it Hall-Patch equation. Okay, so so here the fine grain materials, that is what the one that has small grains, is actually harder and stronger because than the coarse grain, because the former has the greatest total grain boundary area to impede the dislocation motion. Okay, so this is the equation, Hall-Patch equation, where this one is the yield strength. Okay, so the yield strength is actually a function of a constant. Okay, and then so this should be k, yeah. So ky is like a constant, and then multiply with the power of minus half. Okay, the equation is not valid for materials with very coarse and very fine grains, but also grain reduction improve not only the strength but also the toughness of many alloys. Okay, so here is, for example, the graph between the strength as a function of grain size for 70% copper and 30% of zinc, or this one is actually brass alloy. Kuningan, ya, logam kuningan. So brass or kuningan is actually alloy of 70% of copper and 30% of zinc. You can see this is the yield strength in megapascal, and this is the grain size. Okay, so here the yield strength can be increased from around 50, which is at a very low, I think this is about 0.5 something, yeah, there, and then if we reduce it into almost microns here to 5 to the minus 3 to the 10 minus 3 millimeter, or around 5 micron, if we really make it this one here, we can increase the yield strength up to 200 megapascal. Okay, so that is the first one, the first approach. First one is to reduce the grain size diameter. Okay, the second one is using alloys or using solid solution strengthening. Okay, so even we know that, okay, we have pure atoms, and then with some properties, if we add the alloys, or if we add solid solution, it will increase the properties. Okay, so high purity metals are almost softer and weaker than the alloys composed of the same base metal. Okay, so the increasing concentration in the impurity will result in a attendant increase in tensile and yield strength. Okay, so for example, this one, so we have the 3 layer here, and then there is one atom which is has different diameter, maybe smaller. Okay, so in here, so this is the so it, because it has a different lattice there, so the bigger one will will push into this one, and then it will have a lattice strain. We call it would be a lattice strain, regangan pada kisi-kisi kristal. Okay, this is because this one is bigger compared to this one, so it will have a lattice strain. Okay, conversely, if we have the alloy, and then the impurity is actually bigger, in larger diameter compared to the pure one, the atom will also have a lattice strain to the neighboring atoms there, and then it would be a possible dislocation around the lattice strain there. Okay, so here we can see that it is really quite common when we have copper nickel. When we increase the nickel content, the tensile strength will increase, as well as the yield strength. This is similar. The difference is actually the numbers, okay, or the amount of the here the tensile strength is between 200 and 400, while the yield strength, of course, should be lower than tensile strength, which is around maybe 60 to 180. Okay, and the drawback would be the elongation. Okay, so the elongation will reduce from here from 55% into around 30% at the certain 50% nickel content. Okay, so that's why we have a lot of development in alloys. There's so many, I think 100 and 1,000 types of alloys for your phone, for your casing, yeah, for handphone casing, for the laptop casing, for automobile body, and then and many electronic application, and then actually the alloys is actually we added because it also will increase the strength, the yield strength, and also the tensile strength. Okay, and then the last one is the strain hardening. which is we call it cold work. Yeah, cold, which is we do it at room temperature, and then work, so it is we strain it. Okay, and then the plastic deformation is expressed as the original area minus the final divided by the original area multiplied with 100%. Okay, so here we can see the strain hardening from this figure, from 0% cold work like this, and then if we increase it, this become higher in tensile strength and also in this one, but the drawback would be a lower ductility as well as the lower toughness. Okay, so and then so there are three types of strengthening the metal. So in summary, there are three types of strengthening the metal. So can you maybe so who want to say the first one? So what is the first one to strengthening the metal? Anyone would like to?
Is it grain size reduction?
Okay, Ariel, size reduction, that's right. How about the second one? Yeah. Hello. Solid solutions? Yeah.
Yes, solid solution, yes.
Okay, Madaya. Solid solution. And what else? This one, yeah. Cold work or cold rolling, yeah. That is the last one. Okay. Okay, so that is a good thing. Okay, so we want to have a stronger metal. We want to have a stronger and harder metal, and then it can be applied. Okay. However, so this is typical in the manufacturing process. It's called cold rolling, a type of strain hardening processing of metal. Okay, so here I think strain hardening is often utilized commercially to enhance the mechanical properties of metal during fabrication procedure. Okay, so let's next. Okay. So this is there's some exercise. For example, I think you can try it. Yeah, you just need to substitute the equation with some information in here. For example, there are yield strength of iron alloy with this average grain diameter, and then at what diameter the yield strength is this one, and then what grain diameter the yield strength will be this one. So I think you can try it at home. Yeah. The second one, percentage of cold work. If you have the 15 diameter is stretched until 12 millimeters. Okay, you can also try to do it at home. This exercise. Okay, so now after we talk about the strengthening of the metal, so especially there are some drawback in strengthening the metal. Okay, the first one, the plastically deforming polycrystalline material specimen at low temperature will produce microstructural and property changes. Okay, if you look at the microstructure, the microstructure also changes, like it also stretch and also elongated. Okay, and then so there would be a change in the grain shape, and then there's also strain hardening. What does it mean with strain hardening? The energy that we use to stretch, yeah, that will be put into the to the interatomic bond, akan tersimpan di ikatan antar atom. Okay, and also if we when we stretch them, there would be an increase in dislocation density. Yes, there would be a lot of dislocation. Okay, and then some fraction of energy will also expand it in the deformation. So if we stretch something, if we stretch metal, of course that would be the energy to stretch them. Okay, so the energy will be transferred into the deformation. Okay, the deformation in the metal as the strain energy. Okay, and sometimes with the strain energy, some other properties can change as well. For example, the optical conductivity or corrosion resistance. Usually the corrosion resistance will will decrease, so the metal is going to be prone to corrosion if we have a plastic deformation. Okay, so there are some other properties that actually, unfortunately, we don't want that if we do the plastic deformation. Okay, so if it is necessary, the property of the metals can be revert back into the pre-deformation state by adding these three mechanisms, which is a recovery, recrystallization, and grain growth. Okay, so even we have stretched them to make it stronger, but in some cases we can do the crystallization again to our recovery, crystallization, and grain growth in order for the metal have the original the original properties. Okay, and all of this mechanism, it will involve heat treatment. Okay, so we have to heat it up in a heat treatment at a certain temperature, and this process is called annealing, which is a very important part of metal working processes. Okay, so remember, if you remember about the video about the toughness test, yeah, I think a few weeks ago, there are two types of metal at that time. The first one is, we called it strain and age steel, which is so the metal has been strained and also has been aged with steel, yeah, and then it has the toughness test, and the toughness test is will result in a very brittle fracture, akan patah rapuh, and also the energy only, I think, around 13 kilojoule, if you remember, yeah. So we have the first one is strained. Okay, so the strain and age, I remember the energy, they only absorb energy around 13 kilojoule. Okay, and then the second one, the same piece of metal, the same piece of composition, but it has been annealed, it has been normalized still, yeah, if you remember about the toughness video. So the normalized steel, okay, I'm sorry, I didn't open my pad, so I just brought it in my laptop, so it's not really good, that's why. And I remember it's around 182 kilojoule something, so the toughness. So you see that if we do the strain hardening and then we want still the toughness of the metal, we can see here that the toughness is really decreased into 13 kilojoule. So to increase again the toughness, or to increase the ductility again, for they can be formed, they can be change like that, then we do the normalizing or annealing. Okay, and then by using normalized steel, we have 182 kilojoule. Okay, so what happened in the recovery? So there are, I think there are this is an example of one by one. So during the recovery, this internal energy strain in the all the interatomic bonding is actually will be relieved. Jadi dia akan keluar. Okay, so because in recovery is actually in some high temperature, so the energy will heat it up and also will be relieved by dislocation. Okay, so and then you know that at high temperature, relative high temperature of 500 degrees Celsius, for example, we have atomic diffusion will increase as well. The solid atomic diffusion will increase again, so the atom will start to rearrange themselves. Okay, so if we hold it for some time, it will also have some, so they will try to rearrange themselves. Okay, And then during the recovery, there would be some reduction in the number of dislocation, and also dislocation configuration will be produced, and also will have low strain energy. Okay, and then the physical properties such as electrical and then thermal conductivity will recover to their pre-cold work states. Okay, and after that, after the recovery, there is step one. The next step is recrystallization. So recrystallization is actually the formation of new set of strain-free and equiax grain. So the grain is not elongated anymore, but a new grain, equal dimension in all direction, and will have dislocation density, and then will have a characteristic of pre-cold war condition. Okay, and then the recrystallization of cold work metal is maybe used to define the grain structure. So what we have here is actually after if we do the recovery, so recovery is actually in quite high temperature, 500, 600, something like that, and then we wait and then we just keep it for some time, and then they will have a recovery and recrystallization, and after that it will have grain growth. Okay, and then so here, for example, the recrystallization temperature, the temperature at which recrystallization just reach compression in 1 hour, and then for example, the crystallization temperature is around 0.3 in melting point, or 0.7 of the melting point. So if the melting point, let's say at 700, then the recrystallization should be lower than that. So it's still in solid state, but higher diffusion, so all the metals can rearrange, something like that. Okay, so during recrystallization, mechanical properties will change as a result of cold working, are restored to their pre-cold work value, and then the metal will be become softer, weaker, and then more ductile. Okay, so here is this is the explanation. So this one is the picture A is the strain metal. So you can see there are the dislocation lines over here, and then you can see that also it also stretch in that way. So you can see that quite there's lines like that. Okay, and after that we heat it up in some temperature, and then for some time. So what happened is it would be a recovery. So this one still a bit recovery, and then we'll start recrystallization, which is there would be new thick tiny dots here, a lot of tiny dots there, where new tiny dots which is new form, and also it will have a similar properties with the previous one, okay, with pre-cold work properties. And after that the grain will will start recrystallization like this, so bigger than the previous one. And when we have the recrystallization with small grain, and then if we hold it up, the small grain will increase up to like this, and then increase like that, and become this one, so it will grow. Okay, so here this is still in Indonesia, but that's all right. But I think this we can read it here. So for example, if this is the cold work of recovered grain, like a very thin and elongated, and then with this tensile strength and a lower ductility, so we can read the ductility to here. Okay, and then this tensile strength. Okay, so if we heat it up with some temperature, let's say this is the annealing temperature up to here, that will have a recovery, so it will just start to decrease. And after that there would be a recrystallization, where all the strained grain will be replaced by new grains. Okay, and then these new grains will start to form in all the ways, and after that the new grain will grow. Okay, so as it grows, it will increase with the grain size, and also we will have making the ductility going back to the original, while the tensile strength will a little bit lower again. Okay, so here the crystallization degree will increase with time and also temperature, and then recrystallization temperature is the annealing temperature, which has a time around 1 hour, around for this case around 450 degrees Celsius. And for example, if we start with percent cold work of 40%, we know that the recrystallization temperature would be around 500, and then yeah, that would be graph for that one. Okay, and then this is a grain growth. In grain growth, you have after recrystallization is complete, there are strain-free grains will continue to grow if the metal specimen is left at elevated temperature, and this phenomenon is called grain growth. So if we have this grain, this is the grain diameter, this is the time, this is the time for recrystallization, 850, 50 degrees Celsius, 60 degrees Celsius, and so on. And the grain diameter will increase over time, just to increase that one there, yeah. And then this is follows this equation. Okay, so and then the mechanical properties at room temperature of a fine grain metal would be superior those the coarse grain. Oops. Okay, so I think so that's all about the strengthening of the metal. It is the average grain size diameter of the brass, for example, and then you heat it up, check that one, then you can get the constant estimate. Okay, so go back to here. Even though we have we know we need to strengthen the metal by adding some for example by adding the alloy from the beginning, or change the crystallization and then get the lower grain boundaries, grain size, or using cold work. But after that we will in some cases we will need strengthening. Okay, and then to sum up, I would like to show this one in the book again. Wait, okay, so let me stop share and let me open. You can open your Callisto book. Okay. So in the Callisto book there are appendix. Okay, there are appendix in the Callisto book here, and then you may want to see in appendix B about properties. Where is it? Properties of the selected engineering materials. Okay, if you see in the properties of selected engineering materials, there are density, there are modulus elasticity, there are Poisson ratio, strength and ductility, and so on, and plane strain, fracture toughness, and so on. Okay, so you can try to have look this one. Okay, so let's look at the modulus of elasticity. So let's look at let's say alloys. Okay, so in alloys here, for many metal and alloys, for example plain carbon steel, low alloy steel, we know that there's some certain code, and also there is a modulus of elasticity. Okay, and it is actually like just one number. For example, for steel alloy 1040, the modulus elasticity is only in one number, or only 207 gigapascal. Okay, so yeah, and then for example this is stainless steel or cast iron and so on. Okay, and then so that is the modulus of elasticity, E, which is a measure for stiffness. Okay, and then let's look at the appendix B4 about the strength and ductility here. Okay, so the strength and ductility. If you look at the table B4, room and temperature, yield strength, tensile strength, and ductility or percent elongation value for various engineering materials, and let's look at the steel 1040 there. Okay, so you can see that there are a hot rolled, there are cold drawn, that there are annealed, and they're also normalized. Okay, so here you can see that there are treatment of that. So the treatment of the metal will actually influence the properties of those metal. For example, if it is hot rolled, which is it is called it is work, okay, we ditarik ya, di roll, but at a hot temperature, at high temperature, we have the yield strength around 290, okay, in minimum, and then this one is 520. Okay, and then this is the percent elongation around 18. Okay, now and then so if after this or the cold drawn, we can see that the yield strength is much higher. So if it is cold drawn, cold working at a very low temperature, we also get higher tensile strength, but very small elongation, only 12%. Okay, and after that, these two steel alloys is we perform some annealing, or annealing is normalizing or something like that, the heat treatment, which is we leave it at 785 degrees Celsius for some time. We see that here the elongation will improve. So the elongation will improve and the yield strength is still the same. And also with the normalized, of course it's lower than the cold drawn, but we have more elongation. Okay, so it really depends on you or the application. Do we want a very cold drawn and then low elongation, or we still need some elongation because maybe we need to shape those that one there, yeah, the metal material, it depends. Okay, so see, if you look at all the yield strength, the tensile strength, and the ductility, you can see that in steel alloys there are some there's some material condition, and also the heat treatment to that one. Okay, so here also there's some examples. All right, okay, I'm gonna stop it here. Do you have any questions? No, is it clear enough? All right, okay, if it is clear enough, then I would like you to open the EduNext. Okay, so in EduNext I have added some videos, and due to the copyright ID, the copyright things, yeah, I can't record I can't record the video. Okay, so I think the best way for you to learn is actually go to your EduNext, okay, and then open your engineering materials, there, and then in failure mode. Okay, so it's okay. So you can see in this submodule there are some additional video. So we now we're gonna move to the next module about failure, kegagalan. Okay, but before that, before I explain about failure, I would like you to watch some video regarding there are 3 types of failure, kegagalan. Okay, there are fracture, fatigue, and also creep. Fracture, patah. Okay, fatigue is patah lelah, and also creep or mulur. Okay, so you may so I think let's watch this one by yourself, maybe about half an hour. Try which the video that you want, because I just came from the office from ITB, so I need to have a break for salat, yeah. So let us start again around 2:15, okay, after you watching the video. Okay, sounds good, everyone?
Yes, Miss.
Okay, all right, okay. Okay, everyone should have an access with this, the EduNext, and then you don't need to watch all the videos, but you can at least maybe from the beginning or from the fracture and then fatigue, definition, and also the creep. So at least some video, because after this, of course, I will also explain about this one. All right, everyone. So I'm gonna let me pause. Let me wait for the break, just a little bit, and then while you watch, right, I'll be back at 2:50. Okay, everyone. Let's just come back to the class. Okay. So who has watched the failure, the fracture, and also the creep? Yeah, I think uh, you should watch some videos about that one. And then, but before I continue, there's some questions about the videos. Not yet. Okay. I think I can start with the Callister book again. Okay. Yeah. So let's start with the Callister. I think I can start about this one. Okay. 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 So this is the chapter 8, failure. We can see the picture number A first. Okay, about a fracture. Okay, so if you have a coffee sachet or you know, apa ya, like snacks something, yeah. In here there is in the plastic form, the manufacturer has cut the here, yeah, slightly cut there and open here. So, and then when we try to open it, it is much easier. Okay. Okay, so have you ever experienced aggravation of having expend considerable effort to tear a small plastic package? So, of course, and you will notice there is a small incision or cut into the edge. Okay, because there, if we have a cut, if we have a small incision at the edge, there would be a minimal force required to open the package. Okay, so this phenomena is actually related to one of the basic fracture mechanics, which is the applied stress is amplified at the tip of a small incision or not. Okay, and the picture B is actually the oil tanker, which is become brittle in a fracture, in a brittle fracture, just divided by into two because of some of the crop propagation, and then and after that it just failure. Okay. And then there also photograph C, which is a Boeing commercial aircraft experience explosive decompression, and then increasing pressure, decompression again, increasing pressure, and then it lead into structural failure in 1988. Okay. So this is actually caused by metal fatigue. Okay. So so that means here in the failure, we will learn, of course, in the video you also have learned there are three types of failure, three types of kegagalan, which is the first one is fracture, patah, okay, and the second one is fatigue, patah lelah, and the last one is creep or mulur, okay, memanjang, mulur. Okay, so these three phenomena is actually the one that in failure, and of course we don't want to experience that one. Okay, so engineers learn a lot from the past, from many the experience like this, and then try to how can we improve for now. Okay. All right. So let me just I will share screen, but the PPT is still in Bahasa Indonesia, I think. Wait. Okay. So I'm gonna open, but still in Bahasa Indonesia. Okay. Okay, so kegagalan or a fracture. Okay, so we're gonna learn about fracture. Kegagalan is because we don't want them. Of course, we don't want to experience that one. Okay, so the first one, there are three types of failure, which is fracture, patah, fatigue, lelah, and also creep mulur. Okay, so this is an example of metal fatigue. So metal fatigue, we actually, I think the one that really very would be hazardous here, is very dangerous, is actually metal fatigue, because in metal fatigue we don't see any deformation, we don't see any crack, but after that it just broke up. Okay, so here we have some so from the, for example, this is metal fatigue of maybe like one specimen or a piece of metal, and then it's broken into two, and then here there is the origin, and then there is metal fatigue, and then there's final failure. Okay, so here and then before this also we will learn some terms. The first one is a crack or retakan. So crack is actually slightly a failure, which if there is a crack or retakan in it can be inside the metal, or it can be in the surface of the metal. Okay, retakan halus, micro crack, is actually the crack that we can't really see it on by naked eye, but we can check it using microscope, or if you is using ultrasound and so on. Okay, and then a flow, rengat, that's also a term that we're gonna look at, and then there's a vacancy and also a cavity. Okay, and then if you look at the video about the toughness again, you see that there are two types of fracture. The first one is the brittle fracture. The brittle fracture looks like the if you have a chalk and then you make it fracture, patah, the kapur, okay, and then this is a highly ductile fracture. If we try to, for example, we have a very ductile metal, and also this is a ductile fracture, which is a combination between a brittle and a highly ductile, but there's some area around here one. Okay, okay, this is I think this is some in Indonesian, so I think let me just explain with the book then. Okay, I think that's better if I explain with the book. Okay, so here after studying this chapter, you should be able to describe the crack propagation. Oops. Okay, you should explain the crack propagation, and then the strength of brittle material, and then we also will add one more properties about fracture toughness, like you watch in the video, and then this distinction between fracture toughness and plane fracture toughness, and then what is fatigue and also what is creep. Okay, so let me explain with this one. Okay, so there are two types of fracture. The first one is brittle fracture, or maybe the first one is ductile fracture. Okay, in ductile fracture we can see that here is a very highly ductile fracture. So that means the area reduction, it can be almost zero on the tip of those deformation occurs. Okay, an example of highly ductile fracture, usually a pure metal or pure gold. Yeah, if you have a pure gold, it is very soft, and then we can draw it, and then until the area reduction almost very small. Okay, the second one is the brittle fracture without any deformation, so just divided by 2. And then the second one is moderately ductile fracture after some necking. Okay, so the stages in ductile fracture is first it will have a plastic deformation, and then you will have the necking around here. And after that, in the necking, there would be some cavity. Okay, there would be some cavity formation, which is perpendicular to the load, yeah, to the load, so the tensile load, that one. And then those cavity will coalescence together, will agglomerate together to form a crack, like a bigger crack. And after that, the crack will propagate, retakan akan menjalar. So the crack will propagate, and then it will result with a final shear fracture at 45 angle to the tensile direction. Okay, ductile fracture is actually we okay with that, because with the ductile fracture we can know if the metal has will start to do the fracture process, because here before the fracture happens, there would be some deformation here. Okay, so if you investigate your chemical equipment at the plant, and then you notice that there are some plastic deformation, you maybe start being curious. Okay, I think I have to check this equipment. Okay, and even though even if the cavity is inside the metal, you still can see, you still can check it. So we have what we call that non-destructive testing, NDT. Okay, so our friends in mechanical engineering, in materials engineering, know that one very well, where they can there are some certain methods to predict the cavities, the crack inside the metal, by, for example, using ultrasound, using X-ray, or using a dye, tinta. Yeah, so they put some dye into the surface of the pipe. So if there is a very tiny flow or tiny crack like this, the dye will just go through inside the pipe. Ya, akan tintanya akan meresap, and after that we can check it with some detector, ultrasound, and so on, and then we can see some the examination. Okay, that's also similar. For example, in biomedical application, if you want know something happens with your body, you in the MRI, magnetic resonance imaging, we have to put some dye inside our body. Okay, they will insert some dye, and then wait a few minutes until it running around inside our body, and then after that we gonna do the MRI to check if there's something happen with our body, for example. That also happens in mechanical engineering. Okay, so this is the first one, the ductile fracture. Okay, so this looks like the ductile fracture. So this is looks like a cup and a cone fracture in aluminum. There's some, the surface like this. Okay, and the second one is the brittle fracture. The brittle fractures looks like I think we saw it in the video in the toughness test. It's just divided by 2, and then there is no plastic deformation. There is no changes in the diameter, and then the direction for the crack propagation is perpendicular to the tensile load. Okay, so this one. Okay, and then in the brittle fracture, it's called that brittle fracture will take place without any appreciable deformation and rapid crack deformation. Okay, so the difference between ductile fracture, the ductile fracture is quite low. Okay, so there would be a plastic deformation first. We can see it. We can think what can we do to avoid the fracture. Okay, and then and maybe we can change the equipment before have a maintenance, and then we can go again. But however, brittle fracture will take place without any appreciable deformation and will have a rapid crack propagation. Okay, we know brittle fracture more in ceramic, in glass, in building. Okay, so if there's something else, if the building just stay okay, and after that in 1 second it just start collapsing, okay, it is brittle fracture. Okay, the direction of crack of motion very perpendicular to the applied stress, tegak lurus, yeah. So if, for example, go back here, if this is the tensile load, the vertical, and then the direction of a crack would be, of course, would be a horizontal, because it is perpendicular to the vertical one. Okay, and then before that, I need to explain to you about this one, fractographic studies. So in mechanical engineering or material engineering, there's also a branch of study which is called fractographic. So it is a much detailed information regarding mechanism of fracture. Okay, we can use it using a microscope, electron microscope, to check the microstructure of the metal who has a fracture. Okay, this is usually used in, I don't know, air crash investigation. Okay, yeah, in if there is a air crash investigation, or in KNKT, ya, Komisi Nasional Keselamatan Transportasi. So we have a lecturer from materials engineering, almarhum Pak Marjono, ya, almarhum Profesor Marjono. He was the chair of the KNKT, Indonesian Aviation, Indonesian Transportation Safety, and like that. And then how he measure, how he check, for example, what is the cause of, or the root cause for all the accident or airplane accident, usually based on the fractographic study. We see the impact and then check the broken part, and then look at the microscope, and then we check it. So it's called fractographic studies. Okay, so what does it mean with the fractographic studies? For example, in the ductile fracture, it will result in this one, a parabolic shaped dimples, for example, for shear loading. Okay, and for this one, for example, based on an actual tensile load and so on. So there are some knowledge about that one. Okay, and this one also, the photograph characteristic like a V shape, a marking. So this is going to be the origin of the cracking of the crack, yeah. And then this is will propagate really fast, and then that is the direction. So like that. Okay, and then here also, if this is the a piece of metal, and then it divided together, and then brittle fracture of surface showing a radial fan shape ridge, and this arrow will indicate the origin of the crack. Okay, so they can measure so where is the origin of the crack, and then we can have a root cause analysis. Is it because of corrosion? Is it because of too many heavy load on that side, or I don't know, or there's crack previously and it will have a fracture and so on. Okay, so that is the, and then when we for most crystalline brittle material, the crack will propagate, retakan akan menjalar ya, in it can be transgranular or intergranular. Transgranular, that means transgranular because it is very fast. For the brittle fracture, it will may happen along that one, so that all the interatomic bond around here will be just crack as well. Okay, so we can see it on the electron microscope micrograph like this. So this is like one, the one that doesn't have a dark one looks like the boundary, and then this is the boundary which is chopped down into two. Sorry. Okay, so that is so and some alloys crack will propagate along the grain boundary, which is called the intergranular. Okay, so now so there are two types of fracture. The first one is a brittle fracture, and the second one is the ductile fracture. Okay, and now oops, why it's changing. Now let's talk about the fracture mechanics. Okay, the fracture mechanics, I think the one that we watch in the video from the Professor Shackelford also will explain to us about the fracture mechanics. So here, okay, still wait, it's still missing. Wait, why this goes here? I think I need to close this one. I need to close the PDF first. I need to close PDF and then reopen, because it looks like the PDF doesn't respond. Okay. Okay, looks like my PDF doesn't respond it. Wait, or before I check or move, do you have any question or any question regarding the failure? Okay. Wait, still. Okay, then I'll just share the Indonesian version of that one, yeah, because the PDF is not working. Okay. So I've explained this one, and then the next step. Okay, so let's talk about the principle of fracture mechanics. Okay, so the principle of fracture mechanics is the quantification of the relationship between the materials, both the stress and also the flows that cause a crack, and also how the crack will propagate. Okay, kuantifikasi hubungan antara sifat bahan, tegangan, keberadaan rengat pemicu retakan, dan mekanisme propagasi retakan. Okay, so let's look at this. Where is the laser pointer? Okay, let's look at this picture. Okay, in this picture we have a piece of metal. Let's say this is like the thickness of a tank. Okay, and we have a crack. Kita punya retakan. Okay, the crack can be in the middle, or the crack can be on the surface. Okay, if the crack is written in the surface, the length of the crack is A. Okay, and then the radius of the curvature of the crack is called rho t. Yeah, rho t over here. Okay, if the crack is actually happen to be in the middle, so the length of this crack is actually called 2a. Okay, so this looks like an ellipse, so it's called 2a. Well, in here it looks like half of this 2a, so we call it a. Okay, so even though so the stress is actually at the stress here, yeah, at the tip point of the crack. Okay, actually there is a stress concentration, konsentrasi tegangan. Okay, so if we know that the stress is sigma 0, okay, for the tensile load, and then this is the tensile strength, and then the tensile stress, okay, which is sigma 0. Actually, what happened on the tip of the crack is gonna be raised. Okay, for example by sigma m. Okay, so the stress at the tip of the crack, tegangan yang terkonsentrasi pada ujung retakan, so the stress around here, it will be higher than this one. Okay, so that means that the crack will increase the stress, or the crack would be actually equal to, will cause a stress raiser. Okay, so that's why so if you have a piece of metal, and then you have so many crack, that means the stress at the tip of the crack will be higher. Okay, why? Because yeah, this is stress equal to F divided by A0. So if at the tip of the crack, A0 becomes small, and then the stress become higher. Okay, so if we consider, and then the maximum stress at the pada ujung tegangan maksimum pada ujung retakan, or the maximum stress on the tip of the crack, we can call it sigma m, and sigma m is the initial nominal of the tensile load, tensile stress, multiply with the A divided by rho t square root of half. Okay, square root of 2, I mean. Okay, there. Okay, or where sigma 0 is the nominal of the tensile load, nominal tegangan tarik, sigma t equal to the radius of the curvature at the crack, and also A is the half of the internal crack, or the crack on the surface. Okay. So and then we also have so we know the maximum stress, and we also know the concentration stress concentration factor, atau faktor konsentrasi tegangan. Okay, K is just the ratio. So the ratio of the maximum stress on the tip of the crack divided by the initial ones. Okay, so if we have a equipment with a lot of sharp flows, ujung runcing, we have voids, we have internal crack, retakan internal, if we have notches, then there would be a lot of stress raiser as well. Okay, so if we have so many stress raisers, so that when it is higher than the yield strength, and it can hold that one, so it can be fracture. Okay, so in the ductile material, the deformation, plastic deformation will happen if the maximum stress is actually higher than the yield stress. So it will start yielding, it will have the plastic deformation. Okay. Okay, and then and then we also know there is a critical stress, tegangan kritik. The critical stress that we need to so the flow can, or the crack can propagate. Okay, the thing is, if we have a crack and then we have a normal load, like lower than the maximum one, I think we're still okay with that metal. Okay, the metal is okay, there would be no fracture, there would be no failure. Okay, however, if we have a critical stress higher than the stress that's higher than critical stress, then the crack will propagate. Retakannya akan menjalar. Okay, kalau kita bergerak ada di kondisi load lebih rendah dari yang seharusnya, walaupun udah ada retakan, it is okay. Okay, but however, when we have stress which is higher than the critical stress, then the crack, for example, we have the crack like 2 millimeters or 3 millimeters in 2 centimeters of pipe, and after that it will propagate. What happens if it is propagate, and after that it will just broken, it will just fracture. Okay, and this is the critical stress that is used to propagate the crack. It is actually a 2 multiplied with the modulus of elasticity multiplied with the surface energy divided by V, V 3,14, V multiplied with A. Okay, so that one, so that is the critical fracture. So here, jika suatu tegangan tarik pada ujung suatu rengat atau flow lebih besar daripada tegangan kritik, maka retakan menjalar dan akan terjadi fracture. Okay, so if you have a tensile load in one of the flows, and then that is maximum, which is higher than the critical stress, what happens is your crack will propagate, and then what happens is there is a fracture. So we have to ensure that our tensile load, tensile stress should not be higher than the critical stress. Okay, and then this is the there is one more. Okay, so we know toughness is the quantity for us to for metal to absorb energy before it fracture, right? And then there is one more there's one more properties which is called fracture toughness. Okay, fracture toughness is the how the resistance of a material to stand the load if there is a crack. Okay, ukuran ketahanan bahan pada patah rapuh ketika ada retakan. So if we have a crack, it's actually, if we have it is still okay. Okay, if it is lower than the maximum stress, it's still okay. We still can operate with that. We can okay, and the equipment doesn't change or something. But however, if it is higher than the critical stress, then the crack will propagate. So the so we will introduce KC So Kz is actually the fracture toughness, or the quantity or how resistance of a material for a brittle fracture if it is have a crack already. Okay, usually the fracture toughness is very important in ceramic, because in ceramic, if we have some little bit of crack, the crack will propagate, and then it's going to be failure, then it's going to be good for the ceramic. Okay, so usually ceramic, we need to check the fracture toughness of ceramic. Okay, and then here the Y is actually the dimensionless parameter, fungsi ukuran dan retakan, ya. So this Y, okay, and then sigma C is the critical stress, and then square root of VA, which is the ketahanan bahan, ya, the A, or the crack, that one. Okay, and then there are three types of fracture toughness. There are if we have a crack like this, the one that has a tensile load, okay, in that direction, The second one, if we have a crack like this, and then we push the up one over there and the lower one over there. Or this number 3 is we have a shear stress. So on the top we go to that way, and the lower one we go to that way. Okay, so because we always do the testing mostly around this type of testing, so we write that Kc that we like is actually K1C. Okay, Romawi, ya, satu Romawi. So K1C, or we call it plane strain fracture toughness. Okay, so the K, it's not KIC but K1C, and then 1 is actually the crack propagation, follows the model 1 over here. Okay, so here that means this is this number is actually written, and it is actually specific for every materials. Okay, and then here, so if we know this one, if we know the KAC, we know also the Y. In some critical stress, we will know how much or how is the minimum, or what is the minimum crack that we have, in order the material doesn't start to crack and have a failure. Okay, so here so K1C is actually a function of the fundamental properties, is function of the temperature, the strain rate, or the microstructure, and then there's some example how what happened with the sigma Y and so on with the K1C. Okay, so in any materials, we will have the yield stress. Yeah, we have yield stress about, for example, this is metal, ceramic, polymer, and also that K1C. Okay, and then you can see here that for metal is quite okay, for the metal, but however, when you see the ceramic, concrete, beton, yeah, soda lime glass, aluminum oxide, they very have a small KIC. So that means when they have a crack, it's gonna be difficult for them to withstand with those failure, with those fracture. Okay, so and then here when we want to design with this fracture mechanics, there are certain types that we want to see. Okay, first, this one in table 10, this is the one, all the techniques that I explained to you before, how to check the flow and also the crack on the surface or inside the metal, for example, using scanning electron microscope, in the laboratory with dye penetrant surface or ultrasonic subsurface, or using optical microscope or visual inspection or acoustic emission, and also with X-ray even in laboratory or in the field. Okay, it depends. You can cut the pieces in the field and then bring it to the lab and then check it, or you can bring the device into the field and then check like that. Okay, in one very typical chemical plants, for example, we have 1,000 equipment, or including the pipelines, the valve, and so on, and we want to know which one is in have risk or not. There is a type of work that we do usually in mechanical engineering, material engineering, and also chemical engineering. Is called RBI, or risk-based inspection. So we inspect the equipment based on the risk that we see from all those testing. Okay, so when we do the design, if we have a K1C, we know the K1C, so we know the metal, we know how much A is defined. For example, okay, I have this reactor and I found that the A, or the crack, is actually 3 millimeter. How can it stand, okay, with this load? So your critical stress would be this one. Okay, if you operate above this critical stress, of course there would be a failure, there would be a fracture. But if you operate or you put the load around the equipment much lower than the critical stress, then you're gonna be fine. Okay, so it's all about the length of the crack and also the critical stress. Okay, the second one, if you have the K1C, and you also know the applied stress, then you have to check that what is the maximum crack that you're allowed to before it just make a fracture. So this one here, that would be to check. So if so the equipment will be safe as long as it has a crack, but the crack doesn't exceed these millimeters. Okay, I'm gonna stop here. So any question before I move to the next examples? Come on. Okay, it's very quiet. Okay, hopefully quiet means you understand, rather than quiet means you don't understand anything. Okay, so here, for example, this is for spherical tank, pressurized spherical tank. We want to have a design leak before break. So it should have leak before break. So the crack can menjalar sepanjang di tebal dinding. So the crack can propagate as the thickness of the wall. So if the thickness of the wall, if the crack is up to the thickness of the wall, so that would be leaking, tangkinya bocor, okay. And if it's leaking, the fluid can be detecting outside, okay. And after that, we can check and then maybe close the crack, maybe using welding or something. Okay. So so here so this is the design leak before break. Retakan boleh menjalar setebal dinding. So that means we have to calculate that the critical flow or the critical crack would be T, okay, which is the thickness of the tank. Okay, so that means the stress on the wall is actually equal to PR divided by 2T. Okay, this is given. And then the plane strain fracture toughness would be this one. So we know that T also, yeah, from here. And then the tank can't be yielding, tidak boleh luluh. So we change the sigma with the sigma Y, or maximum allowable pressure. And then we will know how much is allowable. Okay. So then here we have the a critical value as well. Okay, so if we have leak before break, the maximum tank would be this one from the KIC. Okay, so here we substitute the T into the KIC and then rearrange the equation to get the pressure. So this is the maximum allowable pressure. Is a function of 2 divided by y square VR, the radius of the tank, and then multiply with the KIC square. We know the KIC of the metal and also the sigma y of those metal. Okay. However, for hazardous fluids, bahan-bahan berbahaya, we can't apply this one. We can't apply leak before break. So we can ensure, for example, tegangan bola dalam dinding, this one here, and then for example we introduce a safety factor, and then we can calculate the thickness. So as long as the crack that we found is less than the critical crack, we can say the equipment is fine. But however, if we find that critical A or is higher than the maximum, we can say that we will say that the equipment is not safe. Okay, because in some time there would be a crack and would be a leaking, and after that there would be a break. Okay, and then there's some example as well. So I think I will upload this the Indonesian version one while still try to translate the English one. Okay, so here if you know the specific energy, the surface energy, you know the modulus of elasticity, calculate the critical stress. Okay, the second question, I think this one I saw a lot in the exam. We have to calculate the stress that causing the fracture, for example, if we have an internal crack of 9 millimeters. Okay, it is not assignment, but let's do it at home so you have some explanation and then more understanding about this one. Okay, I think that's all for today about the fracture. We'll next week we'll continue with fatigue and also creep. Okay. All right, thank you everyone for listening, and then I'm gonna see you again next week.